Hello and welcome. Welcome again to the UCCS Speaker Series. I'm Richard Kravitz, UCCS Director. It's a pleasure to see you all here. As some of you may know, our three themes for the year, around which we wrap many of the Speaker Series presentations, are housing and homelessness, the use of big data to inform California policy, and of course, adapting to climate change and extreme weather. And this talk today, of course, falls under that third theme. It's kind of an irony because much of the reason we're in trouble with climate change is due to energy use and energy production, and yet climate change itself can affect and has implications for that very production of energy that we rely on. And that's kind of the idea, I think, that informs much of the two talks that we're going to hear. We've seen climate change create lots of vulnerabilities in energy production through the diminished snowpack, sea level rise, and even wildfires, as evidenced by the recent interruptions in electrical service, and it looks like we may be looking at another one soon in parts of Northern California. So part of adapting to climate change, our central theme, involves preparing for it and planning. And here we have two experts who know a lot about that topic. So Susan Wilhelm will speak first. She's a team lead for energy-related environmental research at the California Energy Commission. She was previously at the Air Resources Board as a science, technology, and health policy advisor. She has a PhD in environmental health sciences from UC Berkeley, which she obtained after achieving a master's degree in engineering and a PhD a bachelor's degree in physics. And she will provide an introduction and overview of this broad topic. Dr. Wilhelm's talk will be followed by remarks from Dr. Leroy Westerling, who is back for a second encore presentation. This is the third time, I think, that Dr. Westerling has been here in the past 10 years, and that is actually quite an accolade by our standards. We don't invite people back unless they have something important to say, so we're very pleased to have Dr. Westerling back with us today. He's a professor of management of complex systems and co-director of the Center for Climate Communication at University of California, Merced. He's a recognized authority on wildfire, in addition to many other topics, a consultant to state agencies, and he led fire modeling efforts as part of the California State Climate Assessments. His bachelor's degree is from UCLA and PhD from UC San Diego, so University of California all the way. Thank you for that. And he will talk about models related to climate change as they relate to the California state assessments and what they mean for us. So without further ado, we'll start with Dr. Wilhelm.
Thank you for the introduction, and thanks for having me here today. I am going to offer you a general overview of the state of California's work on assessing impacts of climate change on the state. And then we'll look a little bit at some recent results from California's fourth climate change assessment. We'll look at climate projections, and we'll also look at specific results for the energy sector. As Dr. Kravitz mentioned, the energy sector not only causes a lot of climate change, it is vulnerable to it. Then we'll move into state efforts to make these data available to the public for use in informing understanding of vulnerability and risk management. And finally, I'll just have a few remarks on where we're headed before I hand it over to Dr. Westerling. The state of California has been considering, assessing, researching impacts of climate change on the state for 30 years now. The California Energy Commission released a report on the impacts of global warming on California in 1989. This was in response to a legislative mandate by Byron Scher's AB 4420, a really visionary piece of legislation. Since this time, we've done 3 modern assessments, the first of which was released in 2006, and the most recent, which was released in 2018. That was California's fourth climate change assessment. These assessments have been instrumental in informing the state's comprehensive, ambitious, and science-based policy. And I say comprehensive because California not only addresses the need to reduce greenhouse gas emissions, but also to adapt to changes that are on the way and in some cases already observed. So let's step back to 1989. What did we know about how climate change might affect the state at that time? In 1989, the global climate models available were very coarse in resolution. As you see on this figure, if you look at the grid cells, most of California and about half of Nevada, as well as a good bit of the Pacific Ocean, was in a single grid cell. So these models couldn't resolve what might happen within the state. They couldn't differentiate the Central Valley from the Sierra, from the coast. However, based on these models, some general conclusions were made, and these include the expectation that global warming would likely decrease California's snowpack water storage, increase wintertime stream flows, wintertime flooding, and decrease summertime stream flows. As for the energy sector, the report suggested that the electricity sector and the California economy at large might be at moderate risk from global warming. Let's step forward to 2018. What do we know today? The figure you're looking at here portrays the radical increase in resolution of our climate projections for the state. Again, on the left-hand side, you see the level of resolution we had in '89. And on the right-hand side, you're actually looking at a temperature map, but the grid cell is what I want you to look at. You can see that this is very high resolution. It's a 6 by 6 kilometer grid with daily time steps. And the report that you see on the right-hand side of the slide and the links here will take you to a lot of information about these projections, but what I'm going to tell you is that they portray temperature, precipitation, relative humidity, a suite of hydrological variables, and variables related to wildfire-related risks that Dr. Westerling will talk about in a moment. So let's look a little bit at these projections as well as some observed data. One thing that was anticipated in 1989 was a decline in California's springtime snowpack. Well, the black dots here are observed, based on observed data of snowpack. The red and blue lines are projections for the historical and future period, and the dots are actual projection data points. The lines are smooth data. And what we've observed already is that in the western United States, snowpack has already decreased from its historical norm. And based on our climate projections, we expect it to decrease about 1/3 below its historical norm by about the middle of the century. Snowpack is very important for the energy sector. It's historically been a wonderful source of meeting peak electricity demand in the summer when people turn on their air conditioner. But in the future, we will need to plan an energy system that is prepared to cope with less hydroelectric generation in the summertime and an even more variable resource, which is more difficult to manage generally. Another thing we see from our projections is that although the number of days when it rains is expected to be fewer, extreme precipitation is expected to be more extreme and more frequent. So that's right. A drier state with more floods is one way of looking at that. It's a little bit ironic, but one of the reports that contributed to the fourth assessment looked at 13 population centers in northern and southern California and found that across these cities, the frequency of extreme precipitation was increasing and could perhaps be what was a 50-year event historically. What had a 2% chance of happening in any given year historically might be twice as frequent, a 4% chance moving forward. This also matters for the energy system. It's a source of flooding that infrastructure managers have to worry about and can also trigger landslides. And the picture you are looking at on the lower right is Santa Barbara County in 2018 after precipitation that came after severe wildfires triggered catastrophic landslides that took not only life and property, but also had some pretty devastating impacts on the natural gas infrastructure. So, projections developed for the fourth climate change assessment also portrayed what an extended drought might look like in California. This is important to consider because data from the paleo record suggests that persistent droughts that last for a few decades may become more likely in the future. So having a data set to let us see what those impacts would be is important. And for context, I would just note that the drought from 2011 to 2015 cost, in terms of hydroelectric generation that was not available, more than $2 billion. Okay, so let's move away from the projections and look at some highlights from the vulnerability and adaptation studies that were produced by the fourth assessment. And I want to point out on this slide, all of the products of the fourth assessment are publicly available online. And what we're looking at here is the technical reports, but there are also regional reports and statewide synthesis. Okay, so one major way that climate change is expected to affect the energy system is with regard to demand. And there was a study that was performed by Max Alfhammer at UC Berkeley that looked at more than 2 billion utility bills to try and tease out what the impacts of climate change would be on electricity and natural gas bills in the residential sector. And as one might expect, increased penetration of air conditioning and increased use of it is expected to increase both total and peak electricity demand, especially inland and in Southern California. Another research effort undertook a field study to get very high resolution data on levees in the San Joaquin, Sacramento Delta to help us understand how quickly are these levees subsiding and how does that interact with risks associated with extreme storms and sea level rise. What you see in this figure, if you look at the color-coded path along the levees, is that the rate of subsidence varies in space, also varies in time. And the subsidence rates that Ben Brooks from USGS found ranged from about 0.4 to 0.8 inches per year. What this does is it accelerates the time scale at which these levees are at risk of being overtopped by extreme storms coupled with the impacts of sea level rise. And the study concluded that some levees may fail to meet federal safety standards for levee height in the sort of 2050 to 2080 timeframe. And the final slide I'm going to show you from the vulnerability and resilience studies it relates to flood risks for transportation, electricity system, infrastructure. And several studies leveraged huge data sets to look at how might sea level rise, storms, wave run up threaten infrastructure along San Diego in the case of San Diego's coast, in the case of electricity infrastructure. And in the case of the transportation system, they were looking at a terminal in Long Beach where most of Southern California's crude oil is offloaded. And they found that, while right now there's very little risk of flooding, for example, in the Long Beach terminal, by the later decades of the century, there's quite a bit of flood risk. And understanding the time frames at which infrastructure and assets start to face risks helps planners and managers understand what sort of pathways they need to chart, what the timing of their investments might need to be, and how they're going to manage both the technical and financial aspects and the policy and regulatory aspects of adapting to climate change. One last element of California's fourth climate change assessment, in addition to the projections, the technical studies, and the regional reports, statewide reports that I mentioned, is that the fourth assessment made peer-reviewed data sets publicly available, freely available for anyone to use. And we're going to look a little bit at the state's efforts on CalAdapt. This is caladapt.org. This is the landing page. It is a platform for making climate projection data available. These data, again, portray climate at a very local scale. We're not talking about California at large. We're talking about 6 by 6 kilometer grid cells. Data are contributed by many research teams, and they can be explored through interactive tools or downloaded for further analysis at the site. Okay, so I'm going to jump into some of the ways that we can look at climate data on CalAdapt. What you're looking at in this slide is a graph showing how extreme heat might affect a disadvantaged community in Fresno on our current high emissions climate trajectory. You see that in the historical period from 1961 to 1990, which is the period indicated by the blue bracket, there were on average 4 days per year where the maximum temperature was above 106.5 degrees. But moving forward, towards the later decades in this century, when you look at this red bracketed spaghetti, this colored spaghetti, those are climate projections, you're seeing a 12 to 13-fold increase in the number of days above 106.5 degrees in Fresno. And this is a variable number. Some years are hotter than others, and there would be years, according to these projections, where we might have 70 or 80 or more extreme heat days in a given year. We can also look at the timing of these very hot days. On the left-hand side of the graph with the blue bracket, you see that historically, these very, very hot days happened between early June and late September or early September. But moving towards the end of the century, it's all over the place. They could be happening in late May and extend well into October. We also see by the colors of these dots, each dot you're looking at is a day where the temperature exceeded 106.5 degrees. And the dots are getting redder. That's because those days are getting hotter. And there are some days that are projected to be as hot as 120 to 125 degrees on a high emission scenario. Now let's look at extreme precipitation. What we're looking at here is the number of inches of rain that fall in a 3-day period in a 1 in 20 event in Eureka. So that's an event that has a 5% chance of happening in any given year. So it's a big storm, a big 3-day storm. Historically, it was a little over 4 inches, but even by, sorry, it was almost 6 inches. My axis is smaller than yours. But even by mid-century, the 4 climate projections that you see represented by the dots in the middle of the screen show that we expect an increase in the amount of precipitation that Eureka will get in a 3-day extreme event. And by end of century, it could be an approximate doubling. CalAdapt also allows us to look at snowpack, not just from the statewide perspective, but you can look at it from a watershed perspective as well. And here you're looking at the upper middle fork of the American River watershed, which historically has contributed quite a bit to our hydroelectric resources. The gray line on the left-hand side is based on observations, and on the right-hand side we see projections. And these projections are telling us that by end of century, on a high emission scenario, we might expect a 75 to 90+% decline in snowpack in this watershed. My last slide from CalAdapt is an hourly sea level rise tool. So to unpack that, we know that sea level rise is, rising generally. We also know that there are storms and tides and waves that create, hourly fluctuations. So what you're looking at here is a median projection, a high projection, a 95th percentile, and an extreme 99.9th percentile projection. And these curves are showing the fraction of the time that sea level at this point in Sacramento, at this point in coastal San Francisco is above its historical maximum. And what we're seeing is that by about 2095, sea level rise may be above its historical maximum ever observed more than 80% of the time. So what do we do with all these data? The Energy Commission has put it out there on CalAdapt. And there have been many users, but the one I'm going to point to is the investor-owned utilities. The utilities have already used it for infrastructure design and siting. For example, San Diego Gas and Electric has used it for design of a compressor station. PG&E has used that hourly sea level rise data for siting transmission towers in the Bay. Just a few words about looking forward before I pass it to Dr. Westerling. First of all, the need for these projections is only increasing. A recent proposed decision by the California Public Utilities Commission directs investor-owned utilities to California's climate change assessments as a source of data for infrastructure planning and investment. So part of our mission is to produce better projections and to make them more helpful. On making them more helpful, we need more training of users. We need more collaboration to understand exactly how people need this information in order to help them make decisions. We also have ongoing research in anticipation of a next climate change assessment. This research will be providing higher resolution projections that are based on the next generation of IPCC global climate models. They're also going to improve our understanding of wind, which is profoundly important with regard to wildfire risk and impacts of cloudiness on solar generation. And finally, we're working to deliver near and long-term models of wildfire behavior in a changing climate. And I'll pass to Dr. Westerling for that.
So I'd like to put this in a framework I think that Susan has already set us up for very well, and that's to think about a lot of the decisions we make is really insurance, right? So we depend on ecosystem services that are affected by climate variability. And we don't want to experience that variability in the services that we require on a year-to-year basis or a month-to-month or a day-to-day basis. And a good example of that is our water supply. So we build dams, right, that help us smooth out that variability, whether it's seasonal, interannual, or decadal. And the same thing applies to, say, how we build our infrastructure for energy, how we build our homes to be resistant to wildfire, how we manage the landscape for wildfire, how we manage our insurance markets. And all of these practices that we've had in the past for sort of smoothing out the variability in climate and how it will impact services that we consume builds on this idea of stationarity. And stationarity is the idea that you can see some variation from one time point to another, but the probability distribution, the system behind it, is not changing at a speed that would be significant for the resource that you're managing. And so that means you kind of know what the average is and that you're going to come back to it, and you know what an extreme is. In this case, I'm showing that as sort of this typical climate spaghetti, right? And the other point is that when we're doing this kind of investment to smooth out these impacts, it's prohibitively expensive to engineer out all vulnerability. We're always going to have some level of risk to really extreme events, but we take comfort from the fact that we think they're really rare. And so they're high consequence, they have a big impact, but they're not likely to happen at any given time. And those circles there are sort of exemplifying this idea of these extremes that we think we know how rare they are. In that particular case, that spaghetti was drawn from this time series of temperature, not in California, in this case it's in the Rockies, but the different colors are showing different climate model realizations or projections from the historic period to 2099. And then the black jagged line there is showing the instrumental temperature record for the location that I was doing some research on. And the horizontal black line is showing the long-term average. And the thing to notice here is that if you put an envelope around that long-term variability during the instrumental period or before, and then you look at where the projections take us, by the time you've passed about 2050, the coldest year in the future is always hotter than the hottest year in the instrumental record, right? So even in the coldest year after 2050, the average spring and summer temperature is hotter than anything we've experienced in the modern era. So this is the idea that stationarity is dead, right? So this idea that the processes that govern the probabilities of really extreme events that we have to insure against are changing at a speed where if we're building something that's supposed to last a decade or 50 years or 100 years into the future, we can't look to our recent experience to guide us to think about how to make it robust to variability in climate. And then the question arises is, how do we do that? How do you engineer robustness to variability in a non-stationary world? Can we predict future extremes well enough to do so in a reliable way? And the way we're going to get there, and I don't know why my font size changed, is basically we analyze recent changes and then we build models and we project into the future. So all these different climate models and then impact assessment models that Susan was talking about, those are what we need in order to build these systems to be robust to this variability in climate. And now if we look at the recent historical experience with wildfire, you can see that there are obvious trends here. So on the top, I'm looking at forest fires, and at the bottom I'm looking at grass and shrubland fires. And in this particular instance, for this graph, these are on federal lands because that's just convenient. They collect all the data in one place. And what you can see is that decade by decade, the number of these, even though it's highly variable from one year to the next, is increasing. So those horizontal bars are showing you the decadal averages. And every decade there's more fire than the one before. And it's true in both types of ecosystems. It's not just forest fires. It's increasing at a lower rate in grass and shrubland fires, but it's increasing there too. And then if we parse it out into natural ignitions, so lightning ignitions versus human-caused ignitions in black, you can see that in forest fires, the overwhelming majority of the increase, all the statistically significant increase, has been in lightning-ignited fires, not human-ignited fires. Even though most fires in the western United States are ignited by humans, the large ones that are sort of responding to climate change trends tend to be lightning-ignited fires. Now, if we turn and look at fires of all kinds in California specifically, if we're shifting towards more large fires and more area burned in them, you'd expect to see that the largest fire in any given year should be getting bigger. And it turns out it is. So here, I'm merging two different data sets. So on the right is basically a satellite observed based data set telling you the size of the largest fire each year. And on the left, those dashed lines are the three largest fires that we know about from the documentary record over the preceding century. And so they give you an idea of the scale for comparison. So we have observed in recent record, the satellite record, a really dramatic increase in the largest fire each year. You also notice some orange versus red there. The Mendocino fire was actually a complex. It was two separate ignitions that were managed together as a fire. The orange part of that last bar is showing the area that was burning in the ranch fire, which was the larger of the two. So even just considering that one fire in the complex, it was still the largest fire in California state history. And then not too long ago, we had the Rim Fire in the Sierra Nevadas, and we said that that was the largest fire in state history. But actually, the year before, the Rush Fire was larger. It's just we didn't count the area that burned in Nevada because Nevada doesn't count for California. Right? So other things to notice are the ones with stars next to them there, or asterisks. Those are burning in the fall with these like Santa Ana wind or Diablo wind-driven fires. So those are getting bigger, and those are predominantly chaparral and grass. They're not forest fires. On the other hand, the Rim Fire there, that was a big forest fire. And so you've got fires at all different elevations in this record, all different vegetation types, and different times of the year, plume-driven versus wind-driven. They're all increasing in size. And it's not just that we're getting more fires and more area burned in them, they're burning over a longer part of the year. So here, just parsing out the average area burned by month, up through 2000 versus after 2000, you can see that the fire season used to be really sharply peaked with most of the area burning in August. And Now it's really expanded, so the summer, June, July, August, September, October, all have very significant area burned in them. And even November and December are picking up there. Basically, the only months that haven't shown a really big increase are the first 4 months of the year that are the wettest and coolest time of year in the state. And this means that we're managing fire over a much longer period in the year. It also means that the window for doing prescribed fires, when the conditions aren't too extreme, that we can kind of keep them under control to manage the vegetation, is going to be shrinking as this fire season extends. And then the time of year that we're exposed to a lot of air pollution from big fires around the state is also expanded dramatically by months in the recent decades. This is a figure from a paper of mine that made a big splash a long time ago now. But it showed that temperature in the black line there was strongly correlated with the increase in forest fires. So as temperatures warmed up, we got more fire. And a big part of that, mechanics driving that, looking at forest fires around the state, is that warmer temperatures meant earlier spring snowmelt. So if you parse things out, early spring snowmelt years on the left versus late spring snowmelt years on the right, so cool, warm and dry on the left, cool and wet on the right, there's way more forest fires, and they're much larger in the years with the early spring snowmelt, because that lengthens the dry summer season when you can get fuels flammable enough to burn. But interestingly, if I made this figure 10 years before, there was a starker difference between the cool, wet years and the warm, dry years. Part of that difference in the southwest there, that really big fire, that's the Wallow Fire in 2011. When we say it's an early spring snowmelt year or a late spring snowmelt year, it's mostly driven by what's happening in, say, Northern California and the Rockies. The Southwest can be very different. So in that year, the rest of the West was really cool and wet, but the Southwest was really warm and dry. But then you'll also notice that there's just a lot of sort of medium-sized fires now in these years with a cooler, wetter winter and a late spring snowmelt. And we think that's likely that just it's so much warmer in the summer, it still has time to dry out enough from increased evaporation. So the fire risk, even in the years with late spring snowmelts, is increasing as well. Part of this trend in fire is really strongly related to a trend in aridification. So it's not just that the timing of the spring snowmelt is changing. As you warm up temperatures, as you warm up the atmosphere, you basically increase evaporation, right? A warmer atmosphere can hold more moisture. It's drawing that moisture from the soils and the fuels. It's increasing the flammability of the fuel. So if we look at trends in drought conditions or dry versus wet conditions by decade on this same sort of grid that we use for the climate assessments, the first decade, the upper left there, there's no trend over the region. There's some small areas a little bit wetter and a little bit drier, but just what you would expect to see from random chance. The second decade on the upper right, there's this real strong dipole, where it's wet in the southwest and dry in the northwest, and that's really typical of seeing like a transition from La Nina to a really strong El Nino or vice versa, and that's what we had going on in that decade. But then the last 2 decades there, what you see is just a greater and greater spatial extent and greater intensity of aridification, of drier and drier conditions. And this is driven by this increased evaporation as well as changes in the timing of spring. And that is really something that we had anticipated seeing based on earlier versions of these climate model runs. So here is a map for 2000, 2009 showing changes in drought conditions. You'll notice that a lot of the continental interiors and Mediterranean areas, for example, are drying out, and in particular the western U.S. in that projection, and that's what we've been observing. And the other thing to note is that if you look further out in those projections, they're projected to continue to increase in terms of the areal extent and the intensity of this drying out of parts of the continents. And so if warmer and drier conditions in California and the western U.S. have been leading to more fire, we have a lot more of that to contend with in the coming decades. But now, some of the biggest fires that we've experienced in the last few years in California have really been kind of anomalous, right? So they're not forest fires. They're fires at lower elevations where people actually live and burn into places like Paradise or Santa Rosa or Ventura. They're starting quite late in the year compared to what's typical. And these are at elevations and times of year where, you know, it typically gets very dry and warm in the summer. And so these are areas that are quite flammable anyway. So what's going on with that? Is it just temperature? One possibility is that it's increased variability in precipitation. So a lot of what we talk about when we say that precipitation is going to become more variable from the earlier climate change literature is really about getting more extreme rainfall events in terms of more water precipitating per unit area and in time. But as you warm up the planet, you tend to warm up the higher latitudes faster than the equator. So the temperature difference between the equator and the higher latitudes decreases. And that decreasing temperature means that difference sort of slows down sort of the heat exchange or the winds across the atmospheric circulation that's drawing heat from the equator to the higher latitudes. So you go from, there's a potential to go more frequently from a pattern of the jet stream, for example, in the upper image, to a more peaky and trophy one in the lower image there. So bigger peaks and troughs. The idea is that you get weather patterns that set up and are either dry or wet and persist for a much longer period of time, basically parked over your spot on the map. And what we've seen with, and then here's a weather map from a couple of weekends ago, looking just like that, right? And these are the kinds of things that have been setting us up for increased fire risk in the fall. This is showing an estimate of fuel moisture by day of the year for each of the last 40 years in Paradise, California. And they're color-coded by decade. So the most recent decade are in the red there. And you see the Camp Fire occurred in November in the most recent year in that record in a what was a really anomalously dry conditions compared to all the preceding 40 years of records for that time of year. And this is really driven by a failure to get any precipitation of note late in the year. And so that summer dry season basically extended late in the fall. There was a small storm the preceding month and it had already dried out again. And as you lose your fall season storm that used to shut down the fire season, now you get a higher and higher probability later and later in the year of a wind event that can coincide with what are now still really dry fuel conditions. And so you extend the fire season much longer into the fall and into more dangerous wind conditions. So for the assessments, we wanted to be able to capture these extreme events and not just say what's happening to the average area burned, but rather to simulate individual extreme events. So for the fourth assessment, we're doing the maps like you see there on the left, where we're simulating fires, individual extreme fires, based on the topography, the vegetation, the climate, the population and development footprint, and a variety of other things. And those two maps on the left are for the same month in the same scenario. So all the background risk is the same. They're just different random realizations of the same probabilities. And then we can take thousands of those simulations and combine them together to get sort of a heat map where you see how the risk of fire is changing over time. And for different scenarios, you get different increases. They're mostly concentrated at higher elevations where the temperature effects are greatest. How many minutes I got left? 2? All right. So we can look at a variety of different impacts for these. So one is to look at the effect of different climate scenarios combined with fuels management scenarios to look at particulate pollution, from fire. So upper left is the historic emissions from forest fires in the Sierra Nevada. On the upper right is mid-century if we didn't treat the fuels. Lower right is mid-century, so significant climate change, but if we treated the fuels to look like they looked prior to, say, 100, 150 years ago, we'd actually have less emissions even with climate change than we did historically. Owls. So if we look at habitat, it turns out that owls don't like it when you do huge high-severity burns throughout their nest sites. They abandon those nest sites. If you do a lot of fuels treatments that we've simulated in different conditions, you reduce the risk of them abandoning the nest sites over the long term because they still have a mix of the vegetation types and landscape types that they like. Another application is looking at planning in San Mateo County, for example. So we generated these potential fire perimeters that encompass a lot of the county. Our models show a substantial increase in the risk of really big fires in San Mateo County around mid-century. And so we wanted to start mapping those and think about how they impact infrastructure for transportation and energy distribution and emergency management planning in general. And by having these individual events simulated rather than just looking at averages across the state, you can look at different scenarios where you have multiple going on at the same time, intersecting energy grids, say, in different key locations, or different sequencing of events to look at, say, post-fire flood events, for example. And we'll stop there. Thank you.